So it's a pleasure to introduce Stéphane Popinet, who is senior researcher at CNRS and Sorbonne Université in Paris. He's going to present his work on a new multi-layer model for non-hydrostatic flows. So Stéphane, the floor is yours.
Thank you for the introduction. So I'm going to talk about, let's say, recent work. And what I'm trying to do is to, as the title says, find models which can be applied across a wide range of scales. So when I'm saying wide range of scales, what do I mean? So typically, what we would like to find is models which we could apply, for example, to ocean atmosphere dynamics, so scales of thousands of kilometers. And of course, on these scales, you have very large aspect ratios. You essentially have waves for which the wavelength is much longer than the depth. So you are looking at typically non-dispersive long waves. Then if you go to smaller scales, to typically, let's say 10 kilometers, you can look at oceanic wave fields. And of course, in this case, the wavelength is usually much lower than the depth. You are moving to dispersive waves. And of course, in relation to this workshop, you can get wave breaking. So either shallow water wave breaking, a bit like on the coastline here, or even deep water, of course, wave breaking, maybe like here, for example. Then you can push down even lower scales, so it moves down to almost, river, hydraulic engineering type applications. And in this case, it's all the scales of order 10 meters. Of course, in this case, wave breaking, for example, is very obvious in this picture. You can also see these train of wave here, which are clearly dispersive, non-hydrostatic wave trains, for example, in this particular setup. You can even push scales further down, so you can look at film flows. So here we are more in, let's say, engineering fluid mechanics, and the scales are order 10 centimeters. And here you have a combination of typically gravity waves, and in this case, you have also capillary waves. So the question is, can you build a model which can span all these scales? So an approach to do that is to try, what you would like to do also when you build this model, of course, is to relate it to existing models. So for example, classic models, let's say for large-scale oceanic or atmospheric applications, are typically Saint-Venant or shallow water models, where you stack shallow water models. So that's what I've drawn here, pictured here, right? So you have layers, and in each of the layers, typically in a Saint-Venant system, you have the thickness of the layer as a parameter, and of course the horizontal velocity of each layer. And then you stack these layers, and you can describe both the horizontal and the vertical structure. Of course, if you do that, you are missing an important equation, or let's say you assume that one of the equations is replaced by the hydrostatic assumption, and that's the equation for vertical momentum. So if you want to extend that to smaller scales, typically where you cannot neglect vertical inertia, you have to add these blue variables, right? And the blue variables are W, the vertical velocity, and phi, the non-hydrostatic pressure. And phi, more strictly speaking, phi is P over rho, the density, right? So it's a normalized non-hydrostatic pressure. Of course, you have a choice also of coordinates for the system. So you could choose, for example, to express the velocity vector in a coordinate system which follows the layers, or you can express it in the, let's say, the standard or the non-layer based coordinate system, right? The base coordinate system. That's what I'm doing in this particular formulation. Okay, so if you do that, so here I write the equation. So I start with the classic stacked shallow water equation. So of course, the first equation we have here is just a conservation of mass or conservation of volume in each of the layers, right? The second equation is the conservation of horizontal momentum, where eta is the free surface, right? And K, of course, is the index of each of the layers. So you have n equations where n is the total number of layers. If you extend the system to non-hydrostatic, what you need to add is you need to add an equation for the vertical momentum, which is the equation I just revealed here. And so you have transport, of course, horizontal transport of vertical momentum. And then you have this operator here, which is just the difference in pressure between the top and the bottom of the layer. So that's what I write with this operator. K plus 1/2 is the location of the top of the layer, and K minus 1/2 is the bottom of the layer, right? So it's just the vertical gradient of the non-hydrostatic pressure. And of course, the non-hydrostatic pressure also plays a role in the horizontal momentum equation. So you have the gradient of the horizontal, the horizontal gradient of the non-hydrostatic pressure. You have to be a bit careful when you do that because you have to take into account the metrics, so essentially the slope of the layers. And if you do that, you have an additional term which is linked to the slope of the layers, right? Which is expressed like that. So here you see you have the difference of slope between the bottom and the top of the layer. And that comes from your particular choice of coordinate system. Of course, in many systems which look like this term can be neglected, typically by assuming that the slope of the layer is very small. If you do that, of course, you are not solving the full system anymore and you are making approximations. So now we have added two variables. We have added W and we have added phi. So we need to add two equations. We have added only one equation for the moment. So what is the remaining equation? Well, the remaining equation is the conservation of volume, if you want, the fact that the velocity is divergence-free, right? And this is this equation. So we recognize here that the horizontal divergence, right? And the vertical, again, here you have this term, which is the vertical gradient of the vertical velocity, right? And you also recognize here a term which is linked to the metrics, with the choice of particular coordinate system. So what is good about this, this system written this way? Well, the first thing is that it is a consistent discretization of the full 3D Euler equation, right? So you didn't make any approximation, in particular because I didn't neglect the grad Z term. It's clearly connected to the simpler hydrostatic system, right? We can, of course, recognize the hydrostatic system just by crossing out the blue terms. We recover this system. We can even go right back to the single layer Saint-Venant system just by putting one layer, right? It's a system of discrete conservation laws. So, for example, that's in contrast with models you can think of like Boussinesque type wave models, right? Which are not, because of the asymptotic expansion, they are usually not a system of conservation laws. It's numerically efficient, so I'm telling you that. I mean, there are ways of making it numerically efficient. I will give just a few ingredients for this in the next part of the talk. And also you can see it is vertically Lagrangian. So if you look, for example, at the advection equations, right, there is no vertical advection. Why? Because vertical advection is entirely encoded by the layer thickness evolution equation, if you want. So we are really looking at Lagrangian material surfaces moving up and down. So I said it's a plus. Why is it a plus? It's a plus because it's accurate. In particular, it minimizes vertical diffusion. That's very important, for example, for long-term integration of oceanic or atmospheric models, in particular climate models, because you don't want to have vertical numerical mixing, if you want, because in reality, the vertical mixing is very low. So that's a positive property. Negative property, of course, is that as with any Lagrangian system, as the coordinates become very distorted by the flow, you need to do something, right? At some point, it will break. So you need to periodically remap the vertical coordinate. It's not very difficult to do, however, because you are only remapping a 1D system, right? Only 1D vertical coordinate. So you can do that efficiently and accurately. Of course, what's bad in the system written like that is that for the moment, there are too many unknowns. Why is that? It's because you see here, I've introduced the layer interface value, right? K plus 1/2 and K minus 1/2, okay? And of course, we don't know what they are. So we need to make a choice on how to get these values from the values we know, which are on the left-hand side, right? Which are typically layer average values. So how do you make this choice? Well, this is a question which, of course, has been looked at for a long time, in particular by people doing atmospheric or oceanic numerical models. So one person which is very well known who looked at this is Lorentz. So that's the Lorentz of the Lorentz attractor, right? For the chaotic, let's say, simple climate system. And in the same paper, so that's this paper from 1960, introduces the chaotic system, but also it talks about vertical discretization. So if you look at classical atmospheric models, very often they choose what's called the Lorentz grid. And in this case, what you do is that you define your variables like that. So you take phi, the pressure, to be defined as a layer average, and you define the vertical velocity on the interface layers, right? It makes sense because you want to compute fluxes between layers, right? For phi, it also makes sense because you want to compute the gradient of the pressure on the layers. So that's where the connection is. However, I will show that there is a better discretization from several points of view. I mean, it has some drawbacks, but it has a big advantage, which I will discuss a little bit later. which is much more recent and was proposed by Keller in a different context in this paper, and also taken up by Zislema and Stelling in the context of wave modeling in this paper in 2005. So in this particular scheme, you collocate the pressure and the velocity on the layers, and you see that it's connected to the way I discretize the vertical momentum. Why? Because for the vertical momentum, you indeed need the pressure on the layer, right? You are going to compute the gradient as a pressure difference. Okay. So how do you choose which one of these two is better? I suggested that the one on the right-hand side is better, and you can try to find why. So one way to decide or to choose is to compute the dispersion relation, the discrete dispersion relation, or if you want, the dispersion relation of the discrete system. How do you do that? Well, it's simple enough. I mean, you use classic stability analysis. So you take a base flow, you perturb it with this H prime perturbation and with a wave-like solution, right? Kx minus some ET. You inject this in the system, and what you get in return is you get the discrete, or let's say the linear perturbation equation of the discrete system I showed before. So the first equation here, you recognize the layer evolution equation. This is the momentum conservation equation without the nonlinear terms. This is the vertical momentum, and this is the continuity equation. And in a classical way, you compute the determinant of the system, and that gives you the discrete dispersion relation. Sorry. It looks like that, so it's not very surprising. Okay, the frequency squared looks like the true frequency, which is related to J and, of course, J and H0, times a polynomial expression or a rational fraction, okay, of two polynomials where the polynomials depends on K, which is the wave number, right? And of course, if you increase here, it's only for 2 layers, the expression becomes more complicated for more layers, and of course, more accurate. Why? Because you add terms, the order of the polynomials increase, and so you get a better approximation of the dispersion relation, right? So now you can, once you have this discrete dispersion relation, you can look at what they look like for the different schemes. So here, what I display the velocity, the wave velocity, the numerical one, if you want, the discrete one, divided by the exact one, which of course is this expression with the hyperbolic tangent. And of course, a perfect scheme would sit at 1 here. Okay? It would be just a horizontal line. So what you see is that if you use the Lorentz scheme, okay, as a function of the number of layer, when the number of layer increases from 1 to 4 in this case, okay, for very long waves, you get to 1, so it's accurate, which is not surprising. You recover the non-dispersive waves, okay? And then the accuracy decreases. You see it's still quite large, right? It's only 4% error, but of course, it diverges quite abruptly from some typical, let's say, wavelengths, okay, which becomes longer and longer as you increase the number of layers, but you see it doesn't increase very fast, right? Kh equals to 10 is not that large, right? Because you have the 2 pi factor, so typically Kh equals to 10 is wavelengths of the order of the depths, right? So even with 4 layers, you see we don't get a very accurate dispersion relation, okay? If I look now at the Keller scheme, okay, so the other discretization scheme, you see that it is much better. You have a much increased range, and also the rate of convergence is faster, okay? So with the same number of layers, you can really have a very accurate dispersion relation for a much broader range of wavelengths or frequencies, if you want. Okay, so I didn't tell much about that, but how does that compare, for example, with typical Boussinesq model? So, for example, a classic or reasonably classic Boussinesq type model, okay, which is of course typically used to describe dispersive waves, is the Green-Negdy model. So here I take an optimized version of it. Okay, you can optimize the dispersion relation. You see that with 1 layer, you do quite well up to this wavelength, but then it diverges. Okay. And you see that the Keller scheme is almost comparable with 1 layer, and if you just add 2 layers, it's significantly better. Okay, so this is comparable to optimized Green-Negdy. And how does that compare to even better Boussinesq type models? So maybe one of the best Boussinesq models for describing waves is dispersive waves, the model by Chazer et al. So it's a 2-layer Boussinesq model. It's quite complex because, of course, you have the 2-layer asymptotic expansion characteristic of Boussinesq models. But you see, it's excellent. It's perfect, almost right up to Kh equals to 10, but then it degrades also. Okay, so if you take 4 layers, you get a model which is comparable, not as accurate at low Kh, but still comparable using this new formulation. And what you can do also is that all I showed here is for layers which are equidistant, right? And of course, that's not optimal. You can, for example, stagger the layers close to the top of the wave, right, to the free surface. And that gives you a much better description. So here, if I optimize, okay, I just take 3 layers, but they are not now equally distributed. You can get a model which has less than 1% error over a really broad range of wavelengths, or if you want, wavelengths. Okay, so what can you do with this model? I mean, of course, to do something with it, you need to solve it in some way, and you can solve it numerically. So here I just give a brief overview. I mean, so it's done within Basilisk, which is an open source code. You can look at the website, and it's an adaptive model. So Luc Dijker is going to show what we can do for breaking wave, okay, using different model, Navier-Stokes model. And you see that what's nice about it is that you can track quite accurately the wave and the vorticity field using the adaptive mesh. And an important point for the problem we are studying here is that it has an efficient multi-grid solver. So when you solve the non-hydrostatic system, of course, a large part of the cost comes from the Poisson equations, 3D Poisson equation that you need to solve. It's not different for the model I have shown here. But what I've done to make it efficient is that it's multi-grid in the horizontal, and there are vertical line relaxation, which is something which is quite classical, but it leads to quite an efficient system for the system of equation I've shown before. So I said you can apply it to large scale, so that's an example. So here what we do is that we look at tsunamis. So that's the size of the domain. You recognize Japan here, okay? We'll just show that briefly. And okay, so what you see that we initialize with a source, okay, there's only a single layer. It's a dispersive model, so you see wave dispersion quite clearly here, right? And on the right-hand side, you have the mesh adapting from typically 100 meters, right, to hundreds of kilometers, okay? Okay, so I said it's a dispersive model, so we can compare again with green Negdy. Okay, so on the left you have a green Negdy dispersive solution. There's just a zoom on the top part, or sorry, it's later on in the evolution. Okay, that's the one layer non-hydrostatic model I showed before. Okay, so even with one layer, of course, it's dispersive. So that's what you see here. You clearly see wave dispersion, and that's the hydrostatic version of it on the right-hand side. What you see is that the solution is indeed close to green Negdy. Okay, it's a bit different because the dispersion relation is different, and also the dissipation of the model is different. But clearly, the solution match quite well. You can look at the CPU runtime, which of course is important in practice. And you see that the fastest model is actually the non-hydrostatic model. That can be seem a bit surprising, since you would expect maybe hydrostatic, which is simpler, okay, has less equation. There is not the vertical momentum and so on, of course, to be faster, but actually the runtime is shorter for the non-hydrostatic model. And that's linked to a very simple reason, is that because the waves are dispersive, they are slower. Non-hydrostatic waves are slower than hydrostatic waves. So you can use a larger time step to solve the the non-hydrostatic one-layer non-hydrostatic system. You cannot for green Negdy. Why? Because if you remember the dispersion relation, the green Negdy dispersion curve was shooting up, not shooting down. So it meant that the unresolved green Negdy waves are faster than the resolved non-hydrostatic waves. So you cannot use a very short time step, otherwise you will
Stéphane, you have a couple of minutes left.
Okay, good. Okay, so I'm at B-Wave, so breaking wave workshop. So I need to talk about a little bit of breaking. So of course, in these type of models, you need to deal with breaking. What's done in classical Boussinesq style model, right, is that you switch up the dispersive terms, and then you get typically Saint-Venant shocks, which you assume are a good model for breaking. Okay, we cannot really do this here for a 3D layered model. Why? Because if we switch up the dispersive term, we don't get Saint-Venant, right? We get staggered or stacked Saint-Venant, and that's not a good model for breaking. Typically, that's unstable. So what I do for the moment is very simple. Okay, is that I just limit the slope of the slope terms. Yeah, it's a very crude, let's say, breaking parameterization. Okay, why is it crude? Because typically, for example, it will limit steep bathymetries. So here the slope is limited to 1. Okay, so you cannot do bathymetries larger than 45%. Okay, otherwise they get chopped off. It breaks Galilean invariance. I won't give too many details. And of course, you cannot really interpret it as a dissipative term. So clearly, it's a very crude approximation, okay? But still, you can check whether it works or not, okay? And to do that, I'm just going to compare typical, let's say, well, fairly typical breaking wave. So on the top, you have a Navier-Stokes DNS solution, okay, using Basilisk also. So you see indeed breaking with multiple events. And on the bottom, you have the layered version. So you see that right up to the point of breaking, okay, right up to here, typically, you get results which are very comparable. And of course, after that, it saturates. But still, the first thing is that it runs. And of course, the second thing is that it does look, even after breaking, similar to the Navier-Stokes solution. So it's very preliminary results. We can do that in 3D also. So in 3D, of course, it's a bit more interesting. So what happens here is that it breaks first at the top because the water is shallower at the top. Okay, there is bathymetry, and I put shallow water to trigger the breaking there. And that's the type of solution that you get. So you get secondary instabilities, which look, again, realistic. I cannot say they are realistic, but they look realistic. And you get later multiple breaking events and so on and so forth. Okay, so how do we know this could be realistic? Well, for example, one thing we can do is compare with DNS, again in 3D, right? So that's preliminary work, which was done by Jiarong Wu with a postdoc with Luc Dijker. So it's really preliminary, sorry. But you see that indeed we get something which is comparable, at least qualitatively comparable. The obvious thing is that the dissipation, typically horizontal dissipation, seems too low in the multilayer case, which is expected since for the moment we don't have horizontal dissipation in the multilayer model. We only have vertical dissipation. And if you look at the evolution of energy, again, it looks encouraging. You know, it's similar type amount of dissipation, a bit shifted, but again, that's not very surprising. And you can even do that for more complex applications. So what I show here is a simulation by Holstein-Lander with working for Veritas Norway. And what you have here is typically a bit of coastline, Norwegian coastline, and the multi-layer model with 10 layers is applied, and you see multiple breaking events. Okay, that's forced with a spectral code. You have deep water breaking, and also, of course, you have shallow water breaking in this more resolved area. Okay, I'm a bit short on time, so I'm just gonna put this conclusion slide. So just the general conclusion is that indeed we can build models which are applicable on scales which varies typically from meter scale to, let's say, global scales, and they are efficient. And of course, there is still a lot of work to be done to improve, in particular, parameterization of breaking. And I thank you for your attention.
Thank you very much, Stéphane. I think we have 6 minutes, so maybe we can take one question if anyone from the audience wants to ask one, and before we move to the next speaker.
Yeah, Morteza?
Yes, go ahead.
Go ahead.
Yeah, thank you so much for a very nice talk. So there are many multi-layer non-hydrostatic models around. Can you explain what kind of specific feature this model has compared to the existing models?
I guess the main, indeed, there are many models. This one is, I guess, I don't think there is many models which are identical to this one. So the only one I can think of, the closest I can think of, is one by Oliver Frenger at Stanford, which they published a few years back, which is quite similar to this one. I guess the main point here is that it is written as a Lagrangian vertical coordinate. Many of these layers models are Eulerian in the vertical. That's a big difference in the sense that, as I said before, that allows to minimize vertical dissipation, which is very important for oceanic scale applications. So I think this is one of the first, let's say, essentially Lagrangian non-hydrostatic models. Most of the non-hydrostatic layered models are Eulerian in the vertical, and that's an important difference.
We take one more question. Yeah. Are there any other questions?
Can you explain the transversal oscillation that when you show the breaking cases,
yeah,
there were perturbations that were transversal to the crest ridge.
Yes.
So is that basically stream-wise vorticity that is generated?
Yes. Yes.
Can you please, if you can elaborate more on that? How does that stream-wise vorticity generate? What are the?
Yes. So we are really in the if you want the only limitation of the.
Can you show the video again? Is possible?
Okay. So the only approximation we make, I mean, the only limitation of this model in terms of compared to, let's say, a full Navier-Stokes system, right, is that we, of course, we are limited in the slope, right? We cannot do overturning. Otherwise, all the 3D dynamics, in particular the 3D vorticity dynamics under the wave, okay, are represented. So indeed, we will have characteristic typical instabilities, for example, of transverse vortices generating along, longitudinal vortices. We do get these type of instabilities, and that's what you see in this simulation. Indeed, the structures you see correspond to longitudinal vortices, which are secondary instability of the primary vortex, transversal vortex, which you have under the wave. And these motions are properly represented, let's say, by the model. Yes, that's correct.
Thank you.
Okay, so thank you, Stéphane. I think maybe we should pass to